Welcome back to our series for probability theory. I'm Mark Ledbetter, and this is lecture video number 4, counting or enumeration. We're in section 1.2 in the book. Now, when I took this originally, the first time, I got to it and they called it counting, and I thought, oh, this is going to be the easiest section in probability theory. It turns out it's one of the more technical and maybe even one of the more difficult sections if you don't keep up. So please try to follow along, make sure you don't get lost, ask questions, and I'm happy to help you. So the only thing I'm going to review this time is our classical definition of probability for a finite discrete sample space. And this is our motivation. We have to count the number of outcomes in A, number of outcomes in S, so it's all about counting. And we need to come up with some very sophisticated and clean and easy, you might call them shortcuts, for counting complex situations. So everything that we're going to do is based on this multiplication principle, which I'm about to go over. And in this first lecture, we're going to talk about where we're counting things where we care about the order. We're going to do it with replacement and without replacement. And to do this, we need this formal method of proof called mathematical induction. So I'll cover that in the section for ordered without replacement. Then we might not care about the order. We just want unique subsets of things. And so we can do that again with replacement or without replacement. If we're doing it with replacement, then we can talk about the binomial theorem and we can talk about properties of combinations. All right. So let's get started. But all of this will be in the next lecture, which will finish up section 1-2. So I've given you this really nice summary of the main techniques in this section. I received this the second time I took this, which was in grad school, and I found this very helpful, so I hope you'll put this in your lecture notes. We're trying to select R items from N distinct or different items. We can tell them apart. Again, we can do it without replacement, or we can do it with replacement. And you know what? I've got this mixed up. This is without, and this is with. Okay. So without replacement, so we have these different formulas. We'll derive or prove each of them. But everything is set on this multiplication principle or multiplication rule. Let's say we have an experiment E1 and it has N1 possible outcomes. Then after we perform experiment E1, we want to perform experiment E2. And for each of the N1 outcomes in E1, E2 has N2 possible outcomes. Now, if we define an overall experiment E as the performance of E1, then E2, then the number of outcomes in E is equal to N1 times N2, and we can extend this to any M, finite number of experiments. So we just multiply the number of outcomes in each one of these successive experiments, and we get the total number of outcomes in the overall experiment. Okay, but we won't do any proof of this really. You might do it for homework, but we're not doing it in the lecture notes. So the first example is I want to list out all the possible two-digit numbers using 1, 2, and 3. So E1 is select a digit from 1, 2, and 3. So we said all possible two-digit numbers, so we're not, we can use the numbers over again, can't we? So now we're going to say for each digit selected in E1, E2 is select a digit from 1, 2, 3. So here we have N1 is equal to 3. Here we have N2 is equal to 3. Okay? So we have n1 equals 3, n2 equals 3. So I'm getting ahead of myself, n of e is equal to n1 times n2 equals 3 times 3 equals 9. So there are 21 but it says list them all out. So an easy way to list them all out is to use something called a tree diagram. It's also an easy way of counting things, but you have to keep them to relatively simple situations. You can't get too many or you don't have room. Okay, so I'm going to write E1, and I'm going to give myself room here in between. So I have 1. Actually, that's a little close. I'm going to go 1, 2, 3. And then E2, I have to select for each of these digits in E1, I have to select one digit from the 1, 2, 3. And so 1, 2, 3, 1, 2, 3. So I can easily find my sample space from this experiment E. So this is going to be, I just simply combine these digits. So I end up with 11, 12, 13, 21, 22, 23, 31, 32, 33. Now, I'm sorry, use a capital N in this class of S is equal to 9. So it's the same as we had up there. So the sample space, the answer is here, this set. Please read examples 1.2-1 and 1.2-2 in the book. Now, we're going to talk about ordered without replacement first. So we care about the order. The order of something is important here. So we define a permutation as an ordered arrangement of n objects, in different objects, okay? And we can say in a row if you like. Now, we can count those number of permutations of n distinct objects, and that's going to be n factorial. N factorial is defined as n times n minus 1 times n minus 2, and so forth until we get to 2 and 1. Now, there's a definition that you need to know, and don't get confused by this, but how many ways to order or select 0 objects? And we're going to say 0 factorial equals 1. We're defining this. This is a definition, and it's based on that logic, whether you agree with it or not. This is the definition. 0 factorial, this colon and equals says it's defined as 1. Okay? So, those are good things to know. So now we go to an example. How many permutations of the word rehab? Notice that R-E-H-A-B, none of those are repeated letters. So we have distinct 5, so n equals 5 distinct ways to do this. So you can just plug into the formula, but sometimes when you're doing this, it's easier to, I've got 5 different things I'm not replacing here, because I'm going to order these and I'm going to use every one of them. So this will be my first choice, my second choice, third, fourth, and fifth. And so for the first selection, I have all 5 letters that I can choose from. Now, I've already chosen those 5 letters, so for the second one, I'm going to have 4 left. And for the third one, I'm going to have 3, and then I'm going to have 2, and then when I get to the fifth, I only have 1 left. So this is 5 factorial, and that is 120. So there are 120 ways to arrange the 5 letters that are in rehab. So this was ordered without replacement. So without replacement, what if we want to choose R items at a time from N, and they're N distinct items? Well, we're going to write that as NPR here. So NPR, you might want to write this down on your formula sheet somewhere. Now R has to be between 0 and N. It can be 0, it can be N, okay? So I'm going to first derive this like the book does, but this is not a proof. The book acts like this is a proof, but it's not. We need induction for that. So for this derivation, we treat a permutation as a decision. That's kind of messy. With R steps. This is my abbreviation for with. All right, R steps. And R is less than or equal to N. Okay? So first step. Select from N distinct items, i.e., we have N choices. Second step, select from N minus 1 distinct items, and we have N minus 1 choices. Going down to the rth step, and we select from N minus R plus 1 distinct items, or N minus R plus 1 choices. Now you might ask, why do we have N minus R plus 1? So let's take a look at the second step. We would have N minus 1, not N. So basically, I could rewrite this as N minus 2 plus 1. And so minus 2 and plus 1 is minus 1. So these are the same. So when we get down to R, it's instead of N minus 2, it's N minus R plus 1. So that's when I first took the course and saw this the first time, I understood it, but it was kind of difficult for me. I had to think about it a lot. So I thought I'd try to help you out with that. So in PR, we can write this. We're going to say that that is the first, the second, and the rth. And so we've already said we had N minus 1, all the way to N minus R plus 1 equals N minus 1, times N minus R plus 1. Now, NPR, by definition, is N factorial for N minus R factorial. I can rewrite this as N minus 1, all the way down to N minus R plus 1, divided by R N minus R, and all the values below that, that means it's N minus R factorial. Okay? If you need to prove this to yourself, just keep on writing the terms out down to 0 or 2 and 1, right? And then we have N minus R factorial on the bottom. As you can see, we can cancel these out, and we're left with N minus 1, N minus R plus 1, which is what we had up here. Okay. So that derivation is how someone came up with this. And then they were clever enough to figure out the this division here so they could write it very neatly. So as I mentioned, we need to talk about, learn how to do proof by mathematical induction. This is a formal proof method that you'll see in published papers. It's very important to know this. So the first step is the basis of induction. We need to show that the relationship holds for the smallest number of items defined. Okay? Smallest number. That can sometimes be 0 or 1. Those are the two most common, but it could be that we start at 3 or 4 or 5. So be careful. Use the smallest defined number of items. Then our induction hypothesis is we just assume that what we're stating is true. We assume that the relationship is true for an arbitrary, so any, positive integer k, but it has to be finite. There's some cases where we want to use k minus 1 instead of k, because trying to prove something for k plus 1 in that situation might be really, really messy. So sometimes we choose k minus 1, but that's very rare. In this course, if you need to choose k minus 1, I will tell you. Okay, so you don't have to guess. And then the final step where we do all the work is we use step 2. In rare cases, we may have to use step 1 to show that the relationship holds for k plus 1. So if it holds for any integer, positive integer k, and then it also holds for k plus 1, that means it holds for any integer, any positive integer, or all the positive integers. Okay. Now, if we chose k minus 1 in step 2, instead of k plus 1, we'd choose or use k. So now let's do our formal proof with using induction. So the first step is our basis, and I don't need you to write basis of induction, but if you want to for yourself, that is fine. Make this so that you understand what you're doing and when you review this. So 1, note the smallest number is going to be r equals, or k, I'm sorry, k, is this k or r? Yeah, k. So k equals 0. There is only one way to arrange or select or arrange 0 items. 0 factorial is equal to 1. Okay. And so we have to say np0 is equal to n factorial over n minus 0 factorial, which is n factorial over n factorial, which is 1. So that agrees. Now for 2, we're going to say for the induction hypothesis, assume that for some arbitrary positive integer k, with k greater than 0 in this case and less than n. So since we used 0 up here, we don't use it again here, but we know that it holds, but we've already shown it. So for some k that's bigger than 0 in this case, but no bigger than n. So assume that for some arbitrary positive integer k, that the number of ways to select r items from n distinct items is n minus 1 times all the way down to n minus k plus 1, which is equal to n factorial we just showed over n minus k factorial, which is npk. 3. For the induction step, I don't need to write that, but for the induction step, now for k plus 1 items, we have, move this up so I can put my hand on my iPad more easily and write a little neater. We have n minus 1 all the way down to n minus k plus 1. And then we need to go further because we need k plus 1. We need to substitute this in for the k. So this is going to be n minus k plus 1 plus 1. Okay? Which is equal to n minus 1, n minus k plus 1, n minus k. Because n minus k plus 1 equals n minus k minus 1 plus 1. These two cancel out and leave us n minus k. Please keep your sign straight. When you distribute this negative, do it to both of them. All right. And we can say that from step 2, we had that this was equal to NPK, and so that's going to be times N minus K. All right. So I can write out NPK as N factorial over N minus K factorial, and then times N minus K. So I need to cancel out an N minus K. I have N factorial N minus K. So I can pull out the N minus K here, and then I'm left with N minus K plus 1 factorial. Okay? And so notice that if I have N factorial, this is N minus 1 factorial. So N factorial is equal to N times N minus 1 factorial. That's exactly what I've done in this situation. Okay, I've pulled out the N minus K, and then I have N minus K. I'm sorry, this is supposed to be minus 1. Pull out the smallest, yep. Okay. And I will get rid of this so it's not so messy. And then this cancels, and I'm left with N factorial over N minus K minus 1 factorial. Now I need K plus 1, so N factorial over N minus K plus 1 factorial. And this is equal to N P K plus 1, which is exactly what we wanted for K plus 1. So we have proved by mathematical induction that this is true. So please don't forget to scan your lecture notes by midnight tonight. Please make them neat so that you, when you go back, can read them and understand them and help you study for tests, do homework problems. If you have questions, as always, please, you're welcome at the virtual office hours. I'm happy to help you. Or you can email me, and if you need to, we can meet outside the scheduled office hour times. But until next time, think probability theory. See you then.